This is Kevin Sheldrake. I've seen Kevin speak a bunch of times. An interesting guy, has a lot of interesting security knowledge and practices, and he's decided to apply that to some more accessible technology here, and he's going to talk to you about taking over the world with Scratch. So please welcome Kevin.
Yeah. Thank you very much. Oh, wow, that's loud. Thank you very much. I might have my slides appeared on the screen. It looks very blue from here. Ooh. If it says taking over the world with Scratch, then we're good. Okay, that's almost. See, when they said you're first on, I thought this is a great idea because I can't be drunk at this point of the day, and therefore this talk will go. Excellent. Okay, so I am Kev, and I'm talking about taking over the world with Scratch. I've been asked if I can do this quickly so that they can gather some time back during the day. So I'll talk fast, but don't worry, come and ask me questions afterwards if you like. I work as a hacker for a company. I hack into things, and I research hacking tools. That's my kind of job. And in my spare time, I build Lego. This is Scratch, and what I was interested in was, can we connect it to, say, MIDI instruments, or make it talk out loud, or connect it to Lego, or possibly even use it as a hacking tool so that we could hack into other people's computers on a network? You know, what could you actually do with Scratch was my kind of thought. So I got to work on the hacking bit because I thought that was the fun bit, and managed to get it published in this article, POC GTFO, issue OX18. You can find my fun memory corruption exploits for kids with Scratch actually made it into the journal. So I'm very proud, and that gives it some validity, but we'll talk about the other stuff first. So let's talk about Scratch. This is Scratchy or Scratch Cat. I'm sure if you've used Scratch, you'll be aware of the Scratch Cat or Scratchy. He's going to appear all the way through. Scratch is developed by MIT. There's a couple of different versions. So version 1.4 is still around and supported. Version 2 is the one that I use, and you can get an offline version of that, which is written in a different technology. And version 3 is on the way. The last time I looked, it still wasn't operational, but when it comes, it will be written in HTML5 and JavaScript, and it will probably be more whiz-banging and much better. It's taken, a good 10 years to get from the first version to the second. Give them some leeway to get to the next one. But it's been around for a long time, Scratch. Normally, you do it online. So you use your web browser to go to the Scratch website, and then you can just start typing Scratch. You can start scratching, as the terminology is. But when my son wanted a computer, he wanted to upgrade from Scratch Junior on the iPad to Scratch on a computer, I decided that the internet wasn't quite ready for him, and I should protect the world from my son. So I didn't give him internet access. But in order to give him Scratch, I found there's an offline version which will run on your computer. And that has experimental HTTP extensions, which always sounds, anything experimental sounds exciting. So I thought, this has got to be something worth investigating. We'll talk a bit about what Scratch looks like. So I haven't got a laser pointer or anything, so I'll describe things. But on the left of the screen, you've got the stage, which is where your game or your application is kind of running. Down the middle, you've got all your tools, all your blocks, organized into 10 categories. Here we're looking at motion blocks, so you can move a sprite, turn it around, point it in particular directions, etc., etc. And then on the right, you've got the code behind that particular sprite. So the sprite that's selected there is the turtle. This is the code behind the turtle that makes the turtle work. It's kind of object-orientated in the fact that every sprite and the stage itself all runs code concurrently. And it's kind of event-driven. So you can see each section of code starts with an event. Most of those events are when I receive a particular message. And so there's a message-driven kind of system where different objects can send messages and different ones can receive them to know that stuff's happened. If we look at the data section of that sprite, you can see that there's blocks essentially for all the different variables defined for that sprite. Now, 2 of them are ticked. That means that they're visible on the screen, on the stage. So apple count and coin count are actually the two zeros underneath the star and the apple on the left. And those variables can be local to the sprite or global to the whole application. So if we move on to a different sprite, the maze, you can see that some of the variables stay the same. If I flick between, you can see only the apple count and coin count are common between them. That's because they're global variables, not because they're ticked. Tick just means that they're visible, but they're global, so every sprite can access them, read and write to them. Otherwise, your variables are local to the particular sprite or the stage. And you can see that they have different code. Each sprite has its own set of code. So what we can say about Scratch is that we have variables which are either global to the entire app or they're local to a particular sprite. And we have blocks which are basically procedures. So they don't have any return values. So everything you do is by side effects. So you're modifying variables that are like global to the sprite, or you're modifying variables that are global to the whole application. There's no kind of like, I want to call something and get back an answer. You kind of have to set a variable as a side effect and then read the variable, which makes it a bit weird. So I mentioned experimental HTTP extensions. So don't worry about the word experimental, it does actually work. The way you get access to that, on the offline version, normally you would click File to get to the File menu. If you shift click it, you get this super secret File menu, which includes, among other things, import experimental HTTP extension. Now, it's not a widely documented API, but it is documented, you can get to it. The way it works is you end up running a web server on your local machine on a particular port. It has to be on your local machine, it can't be across the network. And that will generate a S2E, a Scratch2 extension file, which describes the extension. And that's the thing we're going to load when we import the experimental extension. And then that will give you extra blocks in the more blocks section. When you use those blocks, it will make an HTTP request to that local host web server to say, I want you to run this block with these parameters. In order to access the variables that the extension offers up, it polls it 30 times a second over this HTTP interface, which is mad. But that's kind of the way it does it. There's no other way of getting it, because everything's a procedure, there's no return values. So it kind of just keeps on polling. So it kind of like pictorially, it kind of works like this. You could make Scratch run a procedure that's in your extension that could modify a variable as a side effect, and then it will poll those variables 30 times a second. So the variable will have changed almost instantaneously in your Scratch environment, and then you can act upon the value that got changed. You might have to have some state variables in order to know when something has changed, in order to know to read the answer, for example. Now, the sort of thing this is useful for is robot arms. I think that's what all Scratch extension frameworks are kind of designed for. And the idea there is that you're either moving the arm, moving the motors that makes the arm move, which have no return values. It's just turn motor on, turn motor off, change speed, etc., change angle. And then we have things like limit switches, which are the reported variables. And again, you want to know when you hit a limit switch pretty soon, hence the idea of polling 30 times a second. So you can sort of see that that's what this is sort of built for. But I thought, what if I kind of plug in a MIDI instrument and I create blocks that turn on notes or turn off notes or send change events? Could you do that? Well, we did, and it works. And it's not the best sequencer in the world, but you can write a sequencer in Scratch. And more interestingly, if you're writing games in Scratch, you could plug in something like an MU50 or some other kind of outboard module that you can pick up on eBay, and you can have really great sound effects for your games. You might not be wanting to like program music, but you might want a few bangs and zaps and helicopter noises and stuff. Equally, could you make it talk? That's another thing. My laptop can talk. Why can't we have Scratch actually speaking out loud? Another one was Lego. So we have a lot of Lego, me and my son, and we have motors and infrared controllers. And that was kind of one of the places where we started, which was, could we get Scratch to control those motors? Because that would be like quite a lot of fun, getting outside of Scratch and actually making something in the real world happen. And finally, can we turn Scratch into a hacking tool and break into somebody else's computer? Because why not? You know, if technology is there to be abused, let's abuse it, you know? I mean, of course, the fun thing with that is that if you're writing data to a socket, that can be a procedure. If you're reading data from a socket, you kind of do it as a procedure, which means read from this socket and put the answer in a variable and then set a state variable to say you've done it, and then check the state variable to see that your answer is in the buffer, and then read the buffer to see what you got back. Polls 30 times a second. It's a perfectly sane framework. So now, writing these extensions is actually quite easy because someone wrote a Python module called BlockX, and you can get that from a GitHub. It's the best way to install it. I wouldn't install it from any operating system packages. I would literally go to the GitHub, download that or clone that repository, and run the setup.py, and it will install, and it works perfectly. Any other way I've found doesn't work so well. But it says on their GitHub that this is abandonware. Like, no one is supporting this any longer, but it actually works. So honestly, it's useful. And they have a link to a tutorial which will explain how to do everything, which I'm going to touch on briefly as we go. So this is kind of how an extension looks in Python. At the top, we're importing that extension, BlockX. The green bit is our class that we're going to define, which is going to be all of our extensions program essentially. So variables that we're going to expose, procedures that we're going to let Scratch call. The yellow line, the descriptor, that describes the extension to Scratch over the API. And then the next bit at the bottom links the descriptor to the object and then runs it so that it appears as a web server so Scratch can talk to it. So I'll give you an example of how easy that actually is. So that all looks a bit complicated, but it's actually pretty straightforward. And I'm going to use say. So if you have a Mac, you'll know that if you type say and then a message, it will speak it out loud. If you don't know that, you should definitely do it, especially if you can log into somebody else's Mac remotely over a network when you're not physically there, and you can make their Mac talk to them. And whisper is one of the voices, which is especially creepy. So the example, my object, my say object, only has one procedure, which is say, because that's the only thing I'm going to do. And it takes two basic arguments: the statement you want it to say and the voice you want it to say with. And if you haven't set the voice, it will set it to Alex, which is one of the default voices. And then it literally calls out to the operating system and runs the say command. -v selects the voice, and it literally says whatever you ask it to say. So that's the whole of the object. The descriptor is slightly longer. The descriptor tells Scratch what it's called, what port it's running on, what blocks it's offering, which is essentially there's one block per procedure in your object, or exposed procedures in your object. And then the dictionary, it lets you create drop-down boxes in your Scratch command. So in the block description, it says say %s with voice %m.voices. So %s means put a string in there. So there'll be a box where someone can type in words, which will be the message. %m.voices means we'll have a drop-down menu, and it will be called voices. And in the bit at the bottom, the dictionary, voices, runs this crazy command, which will go and collect me all the voices that say can say that are English. So we'll have a drop-down menu of voices. And so that is the whole of the code for the say extension, right? And the white bits are pretty common to every extension. All we've done is created an object and created a descriptor and joined them together. That's literally it. So when you run it up, you can then browse to the port it's running on, so port 5000 in this case, and it will give you the option to download the extension. I don't know what a snap block is, I don't really care, but the Scratch2 extension file is the one we want. That's the S2E file. That's what we'll load into Scratch under the experimental extension. So let's do a demo. Here is Scratch. There is my Scratch cat. No, from my mouse. So in here, if I run my extension, oops, which is that one there, it's listening on port 5000. In Scratch, we can shift-click file and import experimental HTTP extension, and it's going to be that one there, the S2E file. I've already extracted it from the web server. And now, actually I'll just close him up a little bit. In the more blocks section, we've now got one extra block. which is say a message with voice and then a voice. So let's make that and then we'll make an event when the space bar is pressed, say that message with voice Alex. And so I can hit. Oh, I don't have any. Why don't I have any audio? Oh no! Since they plugged in the HDMI, I've lost my audio. Right, 1 second. This is clearly a well-tested setup, as you can tell. I guess you can still see the scratch stuff. Yeah. Okay. I'm sure. We go. If I do that and go back to here.
How does this make you feel?
Which is a joke, obviously. Thank you very much. If we change voice.
How does this make you feel? How does this make you feel?
We can select a different
How
one.
does this make you feel?
So, and there you go. So from scratch, we can now make my Mac speak. And on Linux, we can install speak libraries, and we can do the same thing on Linux. On Windows, you can do the same thing if you install something that would make Windows speak. But as you can see, the Python extension was pretty trivial. The actual amount of scratch we need, really trivial. But now you've got an extra element to your game or your application, Scratch is now talking to you. So, we cut back to the slides. I say we cut back to the slides. Ta-da! Right, so now, how do Lego power functions work? Lego power functions are the things with infrared controllers. So there we've got a simple controller and a speed controller. So a simple controller has forwards and backwards for the red channel and the blue channel. The speed controller has rotary dials where you can dial up the speed or dial down the speed, even into reverse for the two different channels. And they talk to that infrared receiver, and that controls motors, for example. It could be lights. I believe there are other things there you might be able to control. We want to control this from scratch. So I'll try and go through this a bit faster than I have done so far, because I'm probably running behind time now. I wanted to listen into that infrared communication between the controllers and Lego in order to work out how it works, so I could do it myself. So I used this thing called an IR toy from Dangerous Prototypes. It costs about 20 quid. It's a kind of simple little tool you can use for listening into infrared. Their software doesn't work very well on Linux. It's written for Windows, and it uses code blocks, which is a horrible kind of environment to compile in. But if you just write some Python, you can talk to the IR toy directly from Linux. So here, the yellow bit is setting up a serial port, the green bit is initializing the IR toy, and the red bit is just reading data that it's seeing. And then point your controller at it, push a button, and see what happens. And what happens is you get a load of hex, which on first view doesn't seem to make a lot of sense. But I noticed that it's a lot of 32-bit words. In fact, it's a lot of 16-bit words, but all of them in pairs. So the upper byte of these 16-bit words being 0, right? So there's clearly timing data of some sort. And if you looked at the last byte of each 4-byte sort of like word, that was the only byte that was really changing. And you can see it changes from about 0E to about 1B. And so clearly that's going to be ones and zeros. So I knocked up a bit of Python to turn that into ones and zeros, and you get this. At which point we then do what we call byte staring, or in this case, bit staring. So here I've got red up channel 1 and red off channel 1, but in actual fact, I would have had every different button combination I could think of so that I could see the binary and compare them and work out how it works. I won't go into the process of how I worked out how it works, but I did work it out, and we'll describe it very quickly. So first of all, there's 4 nibbles, and you can see only a few of them change depending on what you're doing. The first nibble tells you the channel number and if a button's been pushed, or if no button's been pushed, or multiple buttons have been pushed. If you push 2 buttons at once, you get a 0, 0. Who knows why, but you do. And the channel number is 0 to 3, represents channel number 1 to 4 on the actual devices. The second nibble didn't change. The third nibble tells you the button state. This is for the simple controller, I might add, where you've only got up, down. So you could theoretically send a message where the blue was up and down at the same time. I don't know what would happen. I haven't even tried it to find out. But essentially, it's a button mask. That's pretty straightforward. And the fourth nibble is just a checksum. So we XOR together the first three nibbles and invert it. That gives us the fourth nibble. And all that's doing is making sure that the data arrived correctly. That it's got some integrity, so we know that there hasn't been a mistake in transmission or reception. So if we had the red off one, you can sort of see that that fits that protocol. The speed controller, slightly different. So you twist the dial around and you get these kind of patterns. Notice that for it increasing, we've got two different kind of patterns. The first bit changes, and I'll explain that. The first bit of the first nibble is a change indicator. And so only when that change indicator changes does the message get processed by the receiver, which means you can send the same message multiple times and only one of them will be acted upon by the receiver. So you've got message reliability that way. So every time you click one of those rotary dials, it sends the same message 3 or 4 times. And the receiver only receives it once. And then when you click it again, it sends roughly the same message, but the change indicator will have flipped from a 1 to a 0, or from a 0 to a 1. It's quite clever, I quite like it. And then within there, you've also got the channel number. Second nibble tells you if it's a speed message, as in you've changed the speed, or if it's a stop message, as in you've pushed the red stop button. And the fourth bit tells you which channel, red or blue. The third nibble again tells you if it's a speed change or a stop message. I don't know why they doubled that up, but they did. And the fourth bit tells you which direction that controller's going in, clockwise or anti-clockwise. And then the last nibble is a checksum, exactly the same as before. So that's just kind of to clarify, just to show it off. So once we've got that, can we transmit messages? Well, I tried transmitting with the IR toy, and it kept crashing. I don't know if it was the way I was talking to it, I don't know if I was talking too fast, if I wasn't quite talking the right protocol, or whether the IR toy just didn't really like me or something was wrong with the code. But ultimately, I needed to find some other way of transmitting. So I banged together a circuit on an Arduino, and it's simply a high-power infrared LED with a transistor circuit to drive it. Coming off pin D3, which is important because I was using the serial control, the IR remote library, sorry, to actually transmit the data. And that always uses pin 3 on a Nano or a Pro Mini. And I implemented a single byte protocol. So their protocol was 2 bytes, 16 bits. And there's problems with multi-byte protocols because you have to know whether you've got the start of the right bytes. Any multi-byte message system, you need to have some kind of infrastructure around it to know when the messages start and end, and check that you've actually got a proper message and all those sort of things. With a single byte protocol, you get a byte at a time. You can check if that byte makes sense and you can act upon it. Now I could have, and I've since been introduced to Blue Chip's serial control library, which if you're writing anything to do with Arduino, it lets you do multi-byte messages in a really human readable form, and lets you control your thing like it's a router or something. It's a much better protocol. You can get it, this is a plug for his GitHub. It's really good and it works, and it makes everything really simple. But I didn't know about this at the time, so I didn't use it. If you are thinking about implementing these kind of protocols, here's a simple lookup chart to work out which kind of way you should be implementing your serial protocols to your Arduinos. Clearly, don't make a multi-byte protocol yourself. Other than that, either works fine. So my single byte protocol kind of looks like this. I actually only use 7 bits out of an 8-bit byte. Bit 6 tells you which color, which channel we're using, red or blue. The green bits 4 and 5 tell you which channel it is, 0 to 3, essentially 1 to 4 on the actual equipment. Bits 2 and 3 tell you if it's the simple protocol that the button's being pushed up or down. Otherwise, it's 1-1, meaning it must be the speed protocol. And the blue bits 0, 1, tell you in the speed protocol whether it's going clockwise or anti-clockwise, or it's 1-1 to say that it's a simple protocol. So basically, I've squeezed the simple protocol and the speed protocol all into a single byte, which I can just send to my Arduino. And then my Arduino makes the right Lego messages and sends them out. So I have a demo. I didn't bring any Lego with me because all of our motors and infrared receivers are involved in a very complicated remote control car at the moment. It's not quite finished. My son would have probably killed me if I'd brought the Lego with me. So, but I do have some demos, videos. So this is Tom's Sea Monster ride for a fairground, using Lego motors and linear actuators to make the thing go up and down. Programmed and running from scratch. In fact, there is the Arduino and a serial converter. And this one is, I've got multiple videos showing the same thing. This is Tom's automatic crossbow. So I particularly like this one because when we first, what happened was Tom said, can you make something so we can control our models? And I was like, yes. And then 6 months later, I finally did it. And then he was too busy in Minecraft at the time. But some months after that, he was like, Dad, have you got that thing that so we control the motors? And I was like, yeah. I think I was really excited. Took it round, what have you built? And it's like, I've built a motorized crossbow. And so he put all this together by himself. He's using the linear actuators again. It's an amazing thing. So from scratch, it will elevate to a random elevation and then fire the bolt. That's kind of cool. But I'm particularly proud of that. We all like the fact it says police on the side. Like this is this is the future of law enforcement, RoboCop style. But it's quite powerful, and it's quite good fun. So these are the sort of crazy things. We've actually made a lot of other weird, wonderful things with Lego, but that's some examples. So hacking with Scratch. We'll quickly talk about hacking with Scratch. I made an extension that lets me do things like open sockets, read from sockets, write to sockets, bind to sockets, so that I can talk to the network from scratch, which you can't normally do. And I built a descriptor that describes all those blocks so that we could talk it to scratch, and you get blocks that look kind of like this. So you can sort of create a TCP connection to a particular host on a particular port, for example, and then send it some data. These are the more blocks where they appear in Scratch. You've got procedures, predicates, and values. So values obviously give you back a string or a number. Predicates are a true, false value, and they have different shapes, so obviously fit into the right places in Scratch. And the procedures are the things where you instruct Scratch to do stuff, like create a socket or write to a socket or something. And so the way I've got it set up is the web server on localhost running BlockX is the extension, exactly the same as that Say demo or the Lego demo. You just literally plug in the Python and run the thing up, and then you've got these extra blocks you can use. And then that's going to connect onwards to a virtual machine running TinySploit, which is produced by Sawmill Shah of NetSquare under the Exploit Lab workshops. And I've got Sawmill's permission to use it for these kind of demos. And so on there is a vulnerable web server which we could possibly attack. So I did. Now, should we quickly do the demo? Because why not? So if we kill off this Say extension and we run up the socket extension, oops, we come in here. Now, I won't go through the entire work of how you find a bug and then start exploiting it, but if you read the paper in POC or GTFO, it's all in there to explain how to do this sort of stuff. But what I'll quickly do is load in some stuff. So Scratch demo. We need to do that. As you can see, it's quite a bit of Scratch in this particular one. What I'm doing is sending a buffer of changing values to a web server to see where it crashes, and when it crashes, I'll be able to find it in GDB. So there's my actual machine. Hello. Right. We'll quickly connect to the web server with a debugger. And then we'll quickly send this. So we need to fill in have I got an IP address? That was a good point. If I don't have an IP address, we might have to skip this. Okay, tell you what, because I want to speed things up, I'll skip that and we'll go back to the... So what you're seeing on the screen here is the exploit itself. As I say, I can do a demo, and if you come and hassle me later, if you want to see it, I can show you it live how to do this. But from scratch, we did all the work of crashing the service on that virtual machine, and then crashing the service with a pattern buffer so that we can see where it crashed, what the instruction pointer was pointing at the time, what was on the stack at the time. Take those values and plug them into an exploit, and got shellcode simply off exploit DB and chucked it into a variable in Scratch. Had to modify the shellcode because all the shellcode in exploit DB expects bash to be your shell, and in my virtual machine it was busybox, and it needs ever so slightly different type of shellcode. But bung it all together and put in the right values, and before we run it, you can see this is the virtual machine's network services. So we can see that we've got two services, Echo 1 and Echo 2, and we've got a web server on port 18 and an SSH daemon on port 22. Nothing else running. When we run it, this is all the exploit going through the Python. That bit is a whole load of nops to fill up the buffer to get to the point where we can overflow the buffer. That bit there is the return address and a whole load of shellcode, and underneath it is a load more nops just to sort of make sure the thing definitely crashes. And then we go back to and look at the network services listing on the box again. There's one extra service there on port 1337, which is the LEET port. Clearly, this is my exploit running, and that's the shellcode running. So, of course, then what you would do as a hacker is you'd connect to that port using Netcat or Telnet or something and interact with it. But, of course, we're in the world of Scratch. We don't have Netcat because we're not touching the operating system. So we write our own Netcat. And that is the whole of the Scratch you need in order to transmit and receive from sockets, right? So that runs in a loop. You type a command, it brings back the results and spits it in. So if I just make this screen a bit bigger so you can see, this is me logged into Tinysploit over port 1337. You can see what kind of Linux it's running. You can see it's got busybox. I've catted the password file. And so that is actually an exploit running from Scratch in Tinysploit. So, to wrap up, basically Scratch is really interesting as a language. It's really interesting because you don't think it can do very much until you start playing with it, and then you realize that if you extend it, you can make it do pretty much anything that you can make Python do. So there's actually quite a lot of cool stuff you could do with Scratch. But the fact it doesn't have any functions means it's a really bad programming language. It's like learning BASIC on a Spectrum back in the day. You learn a lot of bad practices because you're not thinking functionally. But, it just makes it quirky and interesting. Obviously, we've all used bad programming languages, I guess. You write the extensions in Python, but really trivial Python, like you saw in that say example. Not a lot of Python to actually write, which can be a gateway for kids getting from Scratch into other programming languages. Because once you start writing extensions, you get used to writing Python. Maybe you'll start writing stuff in Python, perhaps. Add GTK to it, you can write for laps. And if you want to do the whole hacking thing, maybe you start learning some x86 machine code. I mean, I went from BASIC on a Spectrum straight to Z80 machine code as a kid, and then to 8086 machine code. I don't see why anyone couldn't go from Scratch to machine code. Why not? So it's a lot of fun, and I definitely recommend that you have a look. My GitHub has the Scratch code on there and the slides, and that's my email address. I'll be around all weekend. Come and find me if you want more of a demo. Thank you very much.
Thanks so much, Kev, for such a fascinating talk. And I've been using Scratch with kids, and yeah, the possibilities are obviously endless, right? So unfortunately, I don't think we're going to have time for questions right away because we need to get to our next talk. But if you want to come and talk to Kev, where can we find you?
Around and about. Just look for me.
All right. In the bar straight after this? Okay, that sounds like a good place. All right. Thank you so much. Please give another round of applause to Kev.